Okay, welcome everybody to another session of our seminar for search of new physics in accelerators and the cosmos. Today we have the presence of the Dr. Yes, PhD, Dr. Saramaggio. I'm going to read I'm sorry, a master in physics
Yes.
from Saramaggio, and I'm going to read a brief presentation about her. So she's a PhD student at the University of Bonn with Cloture. Before that, she did her master in Munich at LMU and TUM, and before that, the bachelor at Sapienza University of Rome. So thank you so much, Sarah, and please go ahead.
Great. Thank you for your introduction. And you see my screen, right?
No, we couldn't
Ah,
see.
we lost it. Okay, let me reshare then. Share. Okay, now you do.
Yes.
Okay, perfect. Yes, so thank you for the introduction and for giving me the opportunity to speak at your seminar. I will not see you, but if you have any things, just let me know if you have question at any point. And today I will talk about canonical differential equation beyond polylogarithms. And this is work that I have done during the past years. And if this word don't make a sense, don't ring a bell to you yet, I hope that they will at the end of the talk. So, first of all, why do we compute amplitudes in general? Well, we know that the LHC will give us new data for the next 2 decades. And in particular, the Higgs sector of the standard model Lagrangian is not yet fully understood. We still have to do measurement in the potential of the Higgs sector, and so also theoretical prediction are very important. So to match the experimental values to the theoretical values. And exactly, so then one of the job of the theorist is to have as possible, precise as possible theoretical predictions. And maybe I just want to sketch what happens at the LHC. And of course, it will be the full process is way more complicated than the thing that I will talk about. We start with proton beams that collide. And what I will mention now in the following will be just the very the high energetic part of the scattering, so where actually gluons and quarks collide. And since it's very high energetic, you can also use perturbative QCD to describe it. But after this, then there is the parton shower, so all these quark and gluons start to radiate soft particles. And then after that, we have the hadronization process. And so then where hadrons actually get formed, and so you need to use non-perturbative QCD. So, okay, if one wants to really talk about the full process at LHC, well, there are multiple steps to take, and of course, I will focus only on one. In particular, for me, is the hard scattering, are part of the scattering. Okay, then having said that, I hope I motivated why computing an amplitude is an important thing to do. And what are the properties of amplitudes? Well, for example, amplitudes have singularities that are, for example, poles. So when we have single particle states that go on shell, so when we have like a production of a particle, then this creates a pole. And in the following, if you see it, I will denote a particle going on shell with this dashed line. It means that I am cutting the propagator where the particle is going on shell. But this is not it. We also have branch cuts, and that is when multi-particle state go on shell. So, but in this case, then the singularity is a bit more complicated. It's not just simple poles, but it's also square root and logarithms. So algebraic, but even transcendental functions. So these are the properties that, at least the singularities that the scattering amplitude has. But on the other hand, we want to compute the scattering amplitude. And so in like modern times, the way that we have to compute a scattering amplitude is to, let's say, split it into two parts. So first of all, we compute all the tensor structure of the amplitude, where by tensor structure, I mean everything that has an index. So for example, in QED, we have the gamma matrices, the carrying Lorentz index, but everything that has an index. So we strip it out from the amplitude. And then we are left with computing some scalar integrals, some scalar families of integrals, because then doing this, we will, our integrals will like form of a basis, let's say every amplitude, then it will be expressed in terms of a basis of integrals that we need to compute, but that are scalar. They don't have any index. And what we have observed, especially at one loop now in the last decades, is that it seems that there is a way to express this integral in a suggestive form. This form is given by some algebraic function at the beginning that carry the information of the poles. So here you will find the poles of the amplitude going on shell. And then there is the transcendental part of the loop calculation that instead carries the information of the multiple particle state go on shell. But overall, this way of writing the amplitude really wants to show the singularity. So it's since the singularities are also the relevant object, it seems that there is it's a very compact and also maybe one of the most compact way to write the amplitude, such that you already know where you are expecting a singularity or where you are expecting a particle to be produced. And integrals that are written like this are called pure integrals. So the integrals that really have are only in terms of the singularities. And so this is what happens at one loop in a lot of examples at one loop. And so then one of the question is what happens when we go beyond one loop? And this is a relevant question because at this point, considering the precision that we have from the LHC, the processes that we need to compute are even like next to next leading order, so 2 loop, but even 3 loop. So going beyond one loop now it's really needed if we want to have some precision calculations. But before going beyond one loop, let me recap when we actually get these logarithms and how do they appear. So if we calculate all the possible, in all the possible way, we cut all the propagators, and cutting these propagators, we get at most algebraic functions, then this means that our integral lives on the simplest possible geometry. And the simplest possible geometry is a Riemann sphere. Just a sphere with some points that we remove from the sphere, so some singularities. And from complex analysis, we know that the only integrals, the only differential forms that we can write on a sphere, such that when we integrate over it, they don't give zero, like when we integrate over a closed contour, well, they are forms of this type. So dt over t minus a, where a is a pole. And here you can see that if you integrate this once, you will get a logarithm. And if you integrate this multiple times, then you will get a multiple polylogarithms. And so then we expect, and we would like to have integrals that when they live on this Riemann sphere, they should look like something like that. So a product of d log, so a product of forms that are of this type, so that are logarithmic singularity. But then since we are in dimensional regularization, because we are in QFT, then we also have some part that depends on epsilon. We will see better later how this affects. But this part comes from the fact that we are in 4 minus 2 epsilon dimensions. But of course, this the form that live on the Riemann sphere don't necessarily have to do with the epsilon part, but then they are connected to it as well. Okay, and an integral that has this form is called canonical. But this is not the only definition that we have of canonical. Indeed, it has been shown that canonical integrals also satisfy very nice properties. So in particular, they satisfy epsilon factorized differential equation. What does it mean? It means that if you take all the integrals that belong to a family, and then you differentiate with respect to external kinematics or masses. So if you differentiate with respect to the parameters that your theory have, then the differential equation has a very nice form in the sense that epsilon comes in front. So here you see epsilon is in the integral, but if your integral looks like this, then all the dependence in epsilon is in front of your differential equation matrix. The differential equation matrix has only simple poles, and this is important because if you have only simple poles, when you integrate, you will get logarithms. And the differential form that appear in this differential equation are independent. This is also very important because when we integrate, again, this differential equation, if some of the forms are dependent, then it might be that doing some integration, there are some additional cancellation. And so this means that the way we write the solution is not the most compact as possible. And if there is this cancellation, maybe it's easy to see them analytically, but if one wants to do it numerically, well, then you have maybe to subtract something that is very similar, and so there can be numerical error, and so then it can be a bit more complicated to track it. And so these three properties are very important for the reason that I just explained, and also they allow you to write the solution in terms of a path-ordered exponential. And this is very nice because in physics, we are not interested in a generic value of epsilon, but we are interested in expanding around epsilon. And so then we can then expand the path-ordered exponential, and at every order in epsilon, we will get some integrals, iterated integrals. And these integrals are very nice because then, since there are only simple poles, well, we have only logarithmic singularity. That is what we want. And at every order in epsilon, since there are only logarithms, then we also have a fixed power of logarithm. So, for example, at epsilon squared, we will only get log to the power of squared, and epsilon cube log to the power of cube, and so on. And this is a property that is called uniform transcendental weight, and this is also very important because if instead of trying to actually compute the integral in this way, one wants to try to bootstrap the integral, so to write the result just looking at the singularities, then it's very important that we know that we have these properties, because then it means that at epsilon cube we can have just some specific function. We don't have not every possible function. And so having this property also reduce the number of functions that we need to put if we want to try to bootstrap the result without computing it. So I hope then I managed to convince you that having an epsilon factorized form, a canonical form, it can be very important when wanting to solve this integral in the simplest and most compact way as possible. But of course, this is not always the case. When we evaluate this discontinuity, so we cut the propagator in all possible ways, we can also get transcendental function. And if we do so, then it means that the space that we are integrating over, it's not just a Riemann sphere, but it can be something more complicated. And the simplest generalization are elliptic curves. And so then we can ask ourselves the same question as before: what kind of differential forms that then corresponds to integral live on the elliptic curve? Well, we can have something similar to before, so we can have just some pole and we can integrate over the pole. And in this case, we have something exactly very similar to before, so our form will be again dx over x minus a, but this time we also have the equation of the elliptic curve. So the elliptic curve can be a polynomial of degree 3, like in this case, or degree 4. And this is a form that we like because, as you see, it's only a simple pole. So it's a pole in A. And so then if we have a simple pole, then this also has logarithmic singularity. But this is not everything that we can get. Indeed, we can integrate along this line or integrate along this line. And these two integration corresponds to two differential forms that have different properties. So for example, the differential form dx over y, this you see it doesn't have any pole. in x, or the differential form dx over y times some power of x has actually double poles. And so then it doesn't look like this additional two form make the elliptic case a bit more complicated than the previous case. And so then one question that we can ask ourselves is if we can keep similar property as before. And the answer is yes, and that's what I will try to tell you in today's talk. And I can already say that the method that I will describe to you has worked in all the geometries that we have encountered so far. So the simplest generalization, as I told you, it's elliptic curve, but you can also have higher genus curves, so curves with more than one hole, but also Calabi-Yau manifolds have appeared in integrals so far, both in QCD, but also in gravitational waves. Okay, then I will try to explain this to you in an example. And probably some of you have already encountered this integral, and this is one of the name in which it's called sunrise. So it's a two-loop integral, and for this talk, I will consider this the first line, the first propagator, to have a to have the mass capital M, and the other two propagators to have the same mass small m. And yes, this is the way to write this propagator. You see the to write this integral, you see the three propagators, so that corresponds to the three propagators here in the graph. But to have a well-defined family of integrals, you also need to include two additional scalar products. But this is just for having a well-defined integral. You can also more or less forget about them. And why is this example particularly nice? Well, because you can divide it into two cases. If you put the mass of the first propagator to 0, we will see that we will only get polylogarithms. While if you put the mass different from 0, you will see that we get elliptic curves. And then we can ask ourselves, can we write this in terms of integrals that make the properties of the scattering amplitude manifest? And especially since we have these two geometries in these two cases, are these properties independent of the geometry? Okay, so let's start looking at it. And we do this doing an integrand analysis. What does this mean? It means, so the way I wrote the integral before, it was in a loop momentum space. Maybe I can show you. Yes, so here we're integrating over the momentum. But there are also other ways of writing an integral. So you can have, they are called parametric representation. So instead of integrating over the momentum, we are integrating over some different parameter. In this case, I'm choosing a representation that is called Bykov. And this means that instead of having the denominators, so we have the denominators 1, denominators 2, and denominator 3, here we have, we just give them a name. So we call Z1 the denominator 1, Z2 denominator 2, and Z3 denominator 3. And here this function B is the change of variable. Then let's start simplifying this integral, because now we have 5 integrations. So the first thing that we can do is to fix the integer dimension. So we would like to have the result in general epsilon, like 4 minus 2 epsilon dimensions, but let's start with putting epsilon to 0. In particular, for this integral, the solution will be nicer if we put d equals 2, but having the dimension in 2 doesn't really affect the result in 4 dimension, because then there are some relation that relate the integral in 2 dimension to the integral in 4 dimensions. So then this is not really, it's not a problem. Okay, we can see, for example, from here that if we put the dimension to 2, then the first prefactor disappears. So it more or less you can see why it simplifies the result. But still, we still have 5 integrations to do. So it's still very, we still have something to do. And so then one thing that we can do to simplify the analysis is to slightly modify this contour. So instead of having a contour that is generic, we can modify the contour to encircle the propagator's pole. So each of these propagator has a pole in 0, because it's just 1 over z1, 1 over z2, 1 over z3. And so we can modify the integral to encircle these poles. And so then we can immediately do these 3 integrations. And this has a particular name, it's called the maximal cut. You can notice that doing this, so modifying the contours such that the propagators are encircled, it's equivalent to cutting the propagator. So to do what I told you at the beginning. And this is a way of simplifying the analysis, but this analysis works also in the full integral. But let's do it in the simplified case. If we do that, then the first three integration are very simple, and then we are left with two integration. So dz4 and dz5. But now you can see that the integration in dz4, it's actually also simple, because here you have two denominators, and they are both simple poles. And so then integrating a simple pole, it will give you a logarithm, so that it's actually what we wanted. And so then integrating a simple pole, it will give us a logarithm, but then we will get some residue from the other factor. And the full result is the following. So we have the logarithm that we wanted, but on the other hand, the residue coming from the other factor gives us a square root over a quartic polynomial in Z5. You can see that in Z5 it's a degree 4 polynomial. And you can try, but this degree 4 polynomial cannot be rationalized. And so then it's actually the equation that defines an elliptic curve. So this is one way of seeing how geometries arise in Feynman integral. But okay, I told you before that we can divide this case into two cases, and let's start with a simple case, putting the mass to 0. If we do so, two of the roots of the elliptic curve collide, and so then they go out and they give you a simple pole in Z5, and two of the other root just stay under the square root. But now this is a square root of degree 2, and so it can actually be rationalized, and we can see it from here. And I'll show you in a moment how you see it. And so then our goal now is to try to find some differential form that are independent. The only parameter that now we can vary is this nu 5 at the exponent. And so let's start with the simplest possible choice. Let's put nu 5 to 0. If we do so, then we have a simple pole in Z5, and that is this. And then we have a branch cut between the two roots of the square root. But now, since it's we have the global theorem of residues, integrating over one, it's equivalent to integrating over the other one. And so then this means that here we can integrate over Z5, and then we get a residue from the other integration. And so again, we are again in the case in which we have a d-log integration, because we have dz5 over z5 that gives us a log. And then putting z5 equal to 0 in the square root, we get a residue. And in this case, then the residue is this, so square root of s times s minus 4m. But this is actually what we wanted, because then we have a sequence of d-log integration with an algebraic function in front. And if we really want, then we can write our good candidate for a master integral as the integral that we just got, but multiplied by the same square root, such that then it simplifies, and this integral j1 is effectively a logarithmic integral. That is what we want. Now, is this everything, or is there anything else that it's independent? Well, you can, for example, see that if you put nu 5 equals to -1, then here at the numerator, we will have z5 to the power of 1, that then simplifies with the z5 at the denominator. And so this means that it creates you can see that it creates a pole at infinity. So instead of having a pole at 0, we now have a pole at infinity, but again, we can play the same trick. And in this case, it's even simpler. The residue is proportional to 1. And so then this integral, it's already in the log form. And so we already found another good candidate. You can play this game again for any other power of nu 5, and you will see that they can all be rewritten in terms of these two integrals. And so, for example, in this very simple case, then we have shown that we can write our integrals as a series of d-log integration times some algebraic function in front. That is what we said at the beginning that we wanted to try to do. Okay, but everything was in for epsilon equal to 0. Let's try to put epsilon back. And this is easy in this case. Why? Well, because if we have integrals of this form, and then we add back the epsilon dependence that I showed you some slide before, well, now you can see that if you expand this in epsilon, because we are interested in the expansion in epsilon, then this doesn't spoil the logarithmic structure, because if you expand this in epsilon, it will just give you 1 plus logs and so on. And so then we will still get only logarithmic singularities. This is what we expect from physics. And moreover, you can show that if you take these two integral, they satisfy epsilon factorized differential equation, so the epsilon goes in front. Then the entries of the differential equation matrix have only simple poles, because indeed they are only d-log entries, and the differential forms are independent. That is what we wanted, and we said that the canonical integral should satisfy. And so this means that then you can write your integral as a path-ordered exponential. And in this case, the integrals that will appear are integral over the log forms. And then these are the so-called polylogarithms. So just chains of integration of logarithms. And this is very nice. We found then a way to make the singularity property of the amplitude evident. Okay, but this was for the simple case of the mass equal to 0. So let's now check what happens for the mass different to 0. Well, in this case, we cannot do much. The square root of the elliptic curve will stay there. And so then we have 2 branch cuts and 2 independent contour. So let's then play the same game and check what happens for different value of nu5. If we start again with nu5 equals 0, then we will get the d-log coming from the previous integration, and now here we just get dz5 over y. But the very nice thing, if you remember from the slide on the elliptic curves, this is just what is called a first kind integral, and this form doesn't have any pole. Indeed, if you integrate over the contour C1, this will give you an holomorphic function. And so this gives you a function without poles. And so then this integral is not that different from the square root that we saw before. And so it doesn't ruin the logarithmic property of the amplitude. And you can just divide by 1 over the result of the integral to have something that, again, it's purely logarithmic. So even for elliptic case, this integral is not a problem. Then we can try putting nu5 equals to -1. And now in this case, we will get a z5 at the numerator. And if you do a change of variable, you can see that this gives you a pole at infinity. But again, you can play the same game. And since this gives you a pole at infinity, it means that there is a simple pole. But then a simple pole, again, doesn't spoil the logarithmic property because it's the pole that we want to have, just a simple pole. And since the residue is again proportional to 1, then we found another good candidate of an integral that has a logarithmic singularity. However, in this case, that is not it. If you put now nu5 equals to -2, then your integral will now be independent with respect to these two. How do we see it? Well, we see it because now this integral has a double pole. And so this integral having a double pole, it cannot be rewritten in terms of these two other forms because they don't have poles. And the problem is that now, since this is a double pole, it means that it's not a simple pole. And so when we integrate over it, we don't immediately get a logarithm. So it seems that now in the elliptic case, there is a problem in doing so, because we will get necessarily not a logarithm. And you can think of it, because if we, for example, integrate once, then we will get a simple pole. If we integrate again, then we will get mixtures of simple pole and logarithms. So we don't get a purely logarithmic object. And the problem It's even greater if we restore the epsilon dependence. So before we saw that the epsilon dependence didn't create any problem, and it's the same case for the two integral here, because if we restore the epsilon dependence, since they were only logarithmic singularities, then again doing the same expansion will not create additional problems. But if we do this here, now this creates additional problems, because then when we try to integrate the double pole, then the integral will also eat the epsilon part. And so then we will get some additional epsilon power that mixes, and so we don't have the logarithmic singularity under control, but we don't even have the epsilon under control. So this integral, it looks like it's really like a bad integral, but it's an integral that we cannot avoid because it's defined by the geometry. So if you have an elliptic geometry, you can't not have this integral. And so we need to find a way to cure it if it's possible. And this is what I want to tell you about. And this is the algorithm that I want to advertise. So it was first found, described 2 years ago and applied only to elliptic case, but then also me and my supervisor and another PhD student joined the project, and in this other paper we applied it to Calabi-Yau, in principle any other geometry. And so then the way this works is that we propose that a good basis that eliminates this problem is a derivative basis. What do I mean? So let's suppose that we found a canonical integral. So by canonical integral, then I mean that it's given by a sum of integrals that are pure, so only logarithmic singularities type, and that are multiplied by uniform transcendental coefficient, so that they don't they ensure that each of this order have the same logarithmic power, let's say. If we now take a derivative of this integral, well, then this integral will not be pure anymore, because if we take a derivative of a logarithm, then we will get the function that is inside the logarithm, it will go outside. And this function is algebraic or rational. And so then the integral is not pure anymore because we have this rational contribution, but it can be made UT, uniform transcendental, if we divide by 1 power of epsilon. Now you see the first term as uniform transcendental weight 1, then the second as transcendental weight 2, and so on. So the property of uniform transcendentality can be kept. We need to remove these additional rational functions. And how do we do this? What we propose is that we multiply by a matrix. How is this matrix defined? Well, first I have to define what we call a period matrix, but this period matrix you can just think of your integrals evaluated in integer dimension. And this period matrix, so basically the integrals, can be split into two parts. A part that is fully algebraic, so it contains more or less like square roots and so on, and a part that is logarithmic. We call the algebraic part semi-simple, and we call the logarithmic part unipotent. And I hope I tried to convey you that what we want to keep, it's the logarithmic part. And so then we can just multiply by the inverse of this semi-simple part so that all the algebraic part goes away. And I want to say that this splitting seems to be very ad hoc, maybe unnatural, but this is known for all the geometries that have appeared so far in the literature. So it's a step that can actually be done for every integral. And so then after we remove this impurity and we are left with some integrals that are more or less only logarithms, then we have to realign the transcendental weight, because as you saw before, if we take a derivative, then we have to multiply by 1 over a power of epsilon, and this can be done with a matrix. But this is not it. So now our integral is only it's a logarithmic type integral, and there is a good epsilon weight, but this doesn't necessarily imply that it's epsilon factorized. So we might have to do some additional rotation by some functions that are a priori unknown. So we just define this additional rotation to contain some functions, and these functions are defined such that the differential equation that the integral satisfies will be epsilon factorized. So basically the goal of this function is to remove all the terms that are not proportional to epsilon. And so then, sorry, these functions are defined by this differential equation, but they can be solved. They can be solved, you just need to solve the differential equation in terms of a series expansion. But contrary to, for example, the objects that are introduced in the semi-simple part, these objects are known. They depend on the geometry, while these objects are not known. They are a priori just some ansatz that we make, but it can be solved. And so then if we do that, for this example or for any other example that we have looked at, we are able to find these integrals that satisfy the epsilon factorized differential equation. Now, we said that there are other important properties. So for example, that the matrix has only simple pole. Unfortunately, we cannot prove yet that our method always gives a simple pole, but for all the examples that we found, it gives simple poles. And we can also not prove yet that the method will always give differential forms that are independent. But for all the examples that we've checked, this is the case. And in particular, you can also ask yourself, well, okay, now we have compute the case with the mass different from zero, but can we do the limit of the mass different from zero to go in the mass equals zero? And what happens in that case? Well, if you follow this algorithm, then you can actually see that if you take the limit, the differential form degenerate to d log forms. So then you are in thinking you get the same result that you would have gotten if you would have started with m equals 0. Okay, but so then this was the example on an elliptic curve. Let me just tell you what happens when you go beyond. It doesn't change much. So still, the very important part is that we start with a good initial basis. So we have always started with some basis that reflected the property of the geometry, and this is what we have to do also when we go beyond the elliptic curves. And then we rotate this initial basis by a sequence of rotation. And so now, instead of having just one inverse of the semi-simple, so one algebraic part that we have to remove, we might have more than one block. And so for each of these blocks, we do the same thing. We remove the inverse of the semi-simple part associated to the block. Then, to get only logarithmic powers. And then we have to do the same. So again, we have to multiply by some epsilon rescalings to realign the weight. And then, again, the differential equation might not be yet in epsilon form. And so we have to multiply by some rotations to ensure that this is the case. Now, the power of epsilon that you need here depends on the dimension of the geometry. It's not too relevant, but the relevant part is that there is one of this last rotation that it's not multiplied by epsilon, and the function that we introduce in this part of the rotation will also be the function that appear in the final differential equation. And so then if we are able to maybe write this function in a simpler way or understand at least the function that appear in this last rotation, it's a great advantage because these are the functions that we will actually see when we want to write the final result. So yes, I hope I managed to convey that these canonical differential equations are more or less important to actually get a result, and that have some properties. And the properties are that the differential equation is epsilon factorized, the entries of the matrix have simple poles, and the differential equation are independent. Now, I have always said this property all together at the same time. So then one question that you might have is, are these property equivalent? And the answer is actually no. Indeed, it has been shown in a paper some years ago that you can have some epsilon factorized basis. So you can find some transformation to go to this basis, but the differential forms that appear in this matrix are not independent. So it's not obvious that if you have a differential equation that is epsilon factorized, it's not obvious that your differential form are independent. But this property is still an important property, so we might want to keep it. And so then we can ask, is there a way to distinguish an epsilon form and a canonical form? And the answer is yes. And one way to do it is using intersection theory. Now, I just want to flash two things about intersection theory. This is not important, but just to give you maybe also another perspective on Feynman integrals. We have seen before that Feynman integrals can be written as, or at least it's what I'm saying in this talk, that they can be written as combination of a multi-valued function. So for example, the function that is elevated to the power of epsilon, and this is multi-valued because it will give you logarithms, different branch cut, and so then it's a multi-valued function, and some differential forms that are single-valued. And so then you can think of these integrals in a more mathematical way. You can think of what is the cohomology spanned by the differential equation that define the integral. And this is called twisted cohomology group. But what I want you to take from it is that a basis of this twisted cohomology group is in correspondence with the basis of the integrals. So if we find the basis of the cohomology group, then we can also find the basis of the integrals. And the only important tool that I will borrow from intersection theory is what is called cohomology intersection matrix. And this is a matrix that is given by the integral over the product between the differential form that define our integrals and the dual differential forms. So the dual differential form effectively for us, it will be just the forms that accompany, instead of this function, the inverse of this function. So they are very connected with the initial differential forms. In particular, you can also see that for maximal cut, the integrals dual, so the dual integrals given by the dual differential forms are actually related to the normal integrals. You just exchange epsilon into minus epsilon. So these objects are very similar to the object that we are talking about. And so this is the only important object that I want to borrow today. Why? Well, you can now, instead of rotating your initial integrals to a canonical form, you can do that with the intersection matrix. So a priori, this intersection matrix, so this product of forms, can be dependent on rational function, so it can be very non-trivial. But the nice thing that it happens is that if you rotate this to a canonical form, then actually the final intersection matrix is a constant matrix. So all the dependence on kinematics goes away. And but to do so, you really need a rotation to a canonical form. So epsilon factorized form here is not enough. And so then this is a very important consequence, because if you know that your rotation goes to go to a canonical form, then you know that you need to have an intersection matrix that it's only given by numbers. But what enters this transformation? Well, we have seen that, for example, in the last rotation, we need to make an ansatz for some function that a priori we don't know. But if you know that in the end you need to get something that is only constant, you know that then this function will have to be related among each other, because they will have to annihilate to only give you some numbers. And so then this can be a tool to actually simplify, or at least try to understand a bit better, what are these objects that enter in the last part of the rotation. And this is a bit more technical, but I just want to flash it. What we have shown after is that you can actually write this last part of the rotation in terms of a multiplication of two matrices. And the important thing is that the second matrix, what we call R, is actually fixed in terms of the object that we already know. So then instead of having a lot of unknown objects, now the only unknown objects are in the rotation O. I will show you an example that I hope it clarifies maybe a bit. So the example that I showed you before, it was the two loops on rice, and this was a well-known integral. So people have solved it maybe 10 years ago, maybe a bit more. But and this is the next loop integral. So instead of being a two loop, now this is a three loop, and with the different masses. And this integral was not solved until a couple of months ago, where me and like my group, we like my collaborators, we solved it. And the same day, also another group solved it. So there are two papers on this result, and yeah, this is just the way of writing this integral. You see, it's already a bit more complicated than the one before. Instead of having 5 propagators, here we have 9, but it doesn't really change that much. And so then let's try to apply what we learned in this state-of-the-art integral. First, we need to find the geometry. So then we can do the same, write our integral in a parametric representation. And the equation that we now see is not an elliptic curve, but it's a K3 variety. So the K3 variety, it's the one-dimensional higher correspondent of the elliptic curve. So the elliptic curve is dimension, a Calabi-Yau manifold at dimension 1, and the K3 variety is a Calabi-Yau manifold at dimension 2. This, it's actually a good news because Calabi-Yau manifolds are very well studied, especially by string theorists. So we know for example, what forms we can associate to a Calabi-Yau manifold. In particular, we know that this form live on what is called middle cohomology, and the Calabi-Yau manifold are known to have here in the 2, 0, so in the n, 0 part of the cohomology, only one form. And so since they are symmetric, also in the H02, they only have one form. And since our manifold here has 4 parameters, then here there will be 4. So we are expecting that there are at least 6 integrals in our family because we have 6 differential forms that live in the K3. And how do we span this? Well, we span them exactly taking derivatives. So we have one holomorphic form, similar to the holomorphic form of the elliptic curve. So the form that was like dx over y, and then we can take derivatives of this. We can take in particular 4 derivatives. So derivative with respect to x1, x2, x3, and x4, because we have 4 parameters. And then we need to take one double derivative for the form that lives in the H02 space. So we are exactly doing the same thing as before. We are just taking more derivatives with respect to before because we have a more complicated space, but effectively we're doing the same. And so then let's then see what happens when we actually try to find the basis of integrals. So now, because of what I just said, we expect at least 6 integrals to show up. But if you run any algorithm, you actually find 15. Why is this the case? Well, we have 4 integrals that are called tadpole, and they belong to a lower sector, so they are fine. And then we actually have 6 integral that corresponds to the K3 manifold, but now if we sum, it's only 10 in total. So we are still lacking 5 integrals. And these 5 integrals correspond to something similar to the integral that always was appearing also before. So this integral with a simple pole at infinity, for example. And so then this integral that have a simple pole also appear when we have more complicated geometry, and they are like similar to the form of the third kind that appeared also before. And so then if we choose the integral in this way, we are actually choosing integrals that are in correspondence with the dimension, with the geometry of our integral. And now we just do the same rotation as before. So we have the semi-simple part, but now it's a bit more complicated. We have, for example, the tadpole part, but they are simple. You have to just multiply by the identity. We have this third kind, again, that as before, similar as before, the residue is always 1. So we just need to multiply by 1. And then there is a bit more the complicated K3 part, but also this is known, and in particular in this paper we showed how to do it for multivariate Calabi-Yau, but this is known. In terms of all objects, that depend on the Calabi-Yau manifold. So all of these objects are known. And then we need to do the rescaling, and the tadpoles and the third kind don't need to be rescaled, but as we saw before, every time that we act with a derivative, we need to have one epsilon power less. And so since we also have an integral that it's a double derivative, then we need to have another epsilon power less. And then we are left with the last transformation to go to an epsilon form. And this is a bit more complicated than before. First of all, we need to have a 1 over epsilon part of the transformation, but this only contains one function, one unknown function. But we have the part proportional to epsilon to the 0 that contains a lot of new functions. So these are 4 that connect the maximal cut to the tadpoles. This is 1, this is 9, and 9. So in total, in the maximal cut, we have 19 additional functions that we don't know a priori. But again, this is not a problem. We can determine them such that the differential equation is in epsilon form. They are defined by first order differential equation, so we can solve them by series expansion. And so in total, in our final differential equation, 23 of this new function will appear. So all of this function will appear. But this is not a problem because we can solve them. We can solve for them. And so then doing this, we get in the end an epsilon factorized differential equation. We can check that the entries have only simple poles, but we cannot check the differential forms are independent, because if we compute this additional function just by like brutally solve for them, so like just getting a series expansion, it's not that straightforward to see that they are independent. And so here it's where the cohomology intersection matrix enter. This is not, it's not really needed for solving it, because we can just solve it like that. But to study a bit better this new object, then it's a very important tool. And so then we can do what I told you before. Now we can consider the cohomology intersection matrix and rotate the cohomology intersection matrix by our transformations. And if we do so, we actually get a matrix that is only given in terms of numbers. And so unfortunately, this doesn't tell us that the forms are independent, because it works only on one way. So we can show that if we have a canonical form, then we need to get a matrix of number, but we cannot show the other way yet. But at least it means that we are on the good way, because here, if we would have gotten some random function, then it means that for sure our rotation was not canonical. And if we also do the splitting that I just mentioned, this can simplify very much the number of functions, because I don't want to go too in depth here, but in this part R of the rotation, we in total will get 9 plus 1 function. So 10 among the 19 functions that showed up before can be written in terms of something that is already known. So really doing this splitting simplifies a lot the also analytic structure of our last rotation. So it's both advantage from a computational point, because then we need to compute less new object, but also from an analytic structure point, we can understand way better this new object that appear. Okay, so then having said that, let me come to my conclusion. I hope I managed to tell you that we have a way to go to a canonical form, and this rotation takes first a geometric input, so we really need to know what is the geometry underlying our integral, and then we have to do a further additional rotation where we include objects that a priori are not known. But if we combine this with some tools from twisted cohomology, actually this part of the rotation that it's not known, it becomes less not known. So we still have something that it's not known, but part of this rotation becomes actually written in terms of known function. So the degree of, let's say, unknown function, it becomes less. So it simplifies the calculation. And what I want to say is this method has been very successful. So the transformation to go to a canonical form has been applied to a lot of elliptic amplitudes already. Then it's also been applied to objects that have a higher genus curve, so a curve with two holes. It has also been applied to black hole scattering, in particular where there are Calabi-Yau appearing in the black hole scattering. It is used for multivariate Calabi-Yau, as we have just seen, for example, this three-loop banana integral. And it has also been applied by other group that didn't have any of our member in their collaboration. Of course, there are still some questions, so we still need to understand better these new objects. And this is not the only method that is out there to do this job, so it would be nice to do a more in-depth comparison with other methods. And then it would be also nice to have proof that we always get what we want, so we always get a canonical form. And then, of course, at some point we have to get numbers, so it would be also nice to see if these functions are, how easy is to evaluate them. And with this, I thank you for your attention.
Thank you so much, Sarah. Thank you so much for the interesting talk. So we have time to questions from the students and the participants online. So if someone have questions, could apply or open your.
Hi, Sarah. Can you hear me?
Hi.
Uh,
Yes.
Thank you for your talk and congratulations for that three-loop calculation.
Thank you.
It was very complicated. All these calculations works for any theory in general. I mean, gravity, QCD, or
Yes, I would say yes. If you manage to write your theory in such a way that you have only scalar integrals, so integrals that don't depend on like gamma functions or stuff. So if you manage to rewrite your integral in a way that you get Feynman integral like type, then yes, it works. This is the only requirement. But for example, there are this group that is using wordline effective field theory, and they are writing the gravitational wave integrals exactly in terms of Feynman integrals, and so they can also use the same techniques. Yes.
okay. And any other thing? Okay, we switch. Hello.
Hi.
I wanted to ask something. It's about the part when you grab the blocks of. There was a part when you the blocks. I don't know if it is true, but it seems like, well, I don't know. What I want is to ask you
This
is
part?
this part. What I want to
Okay.
ask you is if you haven't seen a hidden symmetry, because for me it's strange that you can grab blocks of a matrix and transform it. I don't know if that is a signal for symmetries.
So you mean why I can actually separate this in blocks, if this means something more, something deeper?
Yeah, because it seems very strange with.
Yes, so I would say it's not always obvious that you have this very nice factorization of geometries. But for now, it looks like if you find maybe sometimes you have to find a change of variable, so a better variable, and then you can see the geometries in a then you actually see the geometries. But I don't know if it's a matter of symmetries or that you can really distinguish, like every integral in your family really corresponds to a geometry. I don't know if it's a symmetry, I don't know if it's a symmetry properties, but it might be related to symmetries. I'm not sure about that.
Okay, thanks.
Thanks.
Thank you. More questions here? online questions? We can wait. It seems that there's no more questions, so we want to thank again, Sarah, and we hope that we could have.
Thank you.
Thank you, Sarah.
Thank you.
So, see you.
Bye.